Well, thanks for having me. I'm really sorry that I can't be there. Like many people, I think that the ESF is one of my favorite conferences, one that I've been going to for almost 15 years now. But excited to kick off this session. Sounds like a very exciting session. And so I'm going to be talking today about some work that I carried out at the Jet Propulsion Laboratory with support from a travel grant from Georgia Tech and the Survey leader team here at NASA Goddard. Next slide. So the phenomenon that we're looking at is the solar wind sputtering of material from the lunar surface, in particular, the sputtered secondary ions. And so the solar wind comes in with energies of keV, it sputters off the compositional surface, so you can get all these metal ions, or in water containing areas, we can see potentially the water bearing species as well. And so this talk is focusing on what that looks like for mineral analogs. Next. So the work was, like I said, is carried out on the Radamantes radiation chamber at Jet Propulsion Laboratory. This chamber was outfitted with a phosphor screen so that we could image the incident ion beam, a current post to measure the beam current, and I'm going to be presenting work today looking at sputtering from an amorphous silicon wafer, an iron oxide sample, and a pyrite sample. The chamber was outfitted with a 0.5 to 5 keV ion gun. The work that I'm talking about today will be done with exclusively 5 keV H2 plus ions, a Haydn quadrupole mass spectrometer that was able to detect the sputtered secondary ions, and a translatable cryogenically cooled sample holder that we use to cool down the samples and then deposit the water onto them. So the SIMS measurements were acquired at room temperature after cooling the samples to 100 K, after depositing approximately 20 to 50 monolayers of D2O onto the surface, and then after irradiation and upon rewarming. Next. So the amorphous silicon wafer was formed using a dry thermal oxidation process, and so that had a very well-defined SiO2 composition. But we wanted to double check our iron oxide and our pyrite samples, and we did this using X-ray photoelectron spectroscopy, or XPS, and axillary fluorescence, or XRF. We can see from the table of the compositions here for the iron oxide and the pyrite that we don't have pure samples, and instead the iron oxide was composed of predominantly Fe2O3, but there were also some ilmenite inclusions, Ti2O3, and as well as some calcium and aluminum inclusions in there. The pyrite we see was predominantly FeS2, although the surface compositions of both of these samples differed a little bit from the expected bulk compositions. That silica came from the dry polishing preparation that we used in these samples. So before analysis, the samples were dry polished and then rinsed using isopropyl followed by water. But we found that some of that silica remained on the surface. So that Si, which we see in the spectra for these samples, was due to the dry polishing. And although that's not giving us an idea of exactly what these pure mineral samples would do, it is a little bit more relevant to a mixed planetary surface. Next slide. So the first results that I'm showing are for the amorphous SiO2. And we see that at room temperature in the green spectra, we see exclusively just the silica group ions. So Si, SiH plus, and then some SiOH plus, a small, potentially due to the isotope of silicon. This is on a log scale. And so in the green spectra, this is most likely due to the silica isotope logs. Then following the deposition of about 50 monolayers of water, we see exclusively water group ions. And in particular, we see the H2OD plus, D2OH plus, and D2OD plus. The reason that we're seeing a mixture of the H2Os and the Ds is because there was a little bit of background deposition of water from the chamber, and so you do have some H2O mixing in with the D2O, even though it's predominantly D2O, as well as the fact that there are chemical reactions occurring in between the incident hydrogen ions and the deposited D2O. After irradiation, we then see a mixture in the red spectra here, a mixture of the water group ions as well as some of these silica group ions that are appearing once the substrate is exposed due to sputtering. In particular, we see a large component of SiO-D plus forming in those dose sputtered spectra, suggesting that there is actually a chemical reaction occurring in between the deposited D2O plus and the irradiated Si surface. Next slide. Similar for the iron oxide, we see that there are some of these inclusion species in the spectra. They are present at somewhat higher abundances than you expect based on the composition of the sample, but this is due to the fact that the Mg and the Al and the Ca and to some extent the Ti have much lower ionization potentials than the predominant Fe plus species. And so even though there's a smaller relative abundance of these in the measured compositions of these samples, you see a larger abundance of these in the sputtered secondary ion signal due to their lower ionization potential. Again, we see very similar patterns where in the fresh or the room temperature, the green spectra, you see only the substrate ions. Then after depositing the D2O, we see these water group ions. And then after sputtering for a while, we see that you get a mixture of the two. And in similar fashion to the SiO2, we see that in these dose sputtered spectra, we're seeing a relatively an increased abundance of the Fed plus species for the iron oxide. Next slide. And then it's very similar again with the pyrite. We see that for the room temperature, the green spectra, we see predominantly just the Fe plus, although there are small abundances of some of these inclusion species, the Al and the Si. After depositing, we see just the D2O plus. It's kind of interesting here that we see different relative abundances of the various water group species depending on the substrate composition, suggesting that there is some substrate dependence happening for the relative abundance of the water group species. After sputtering for a while, we do start to see those substrate ions reappearing in the red spectra. And in particular, we don't really see for the pyrite the formation of many deuterated species. And so there's no clear increase except for the SiO-D plus here at mass 46. We don't really see much of an increase in the deuterated species for the pyrite substrate. Next. Interestingly, we see that when we track the relative abundance of the various ions over time, we see a peak in the water group species. And so the solid lines are showing the water group species. The dotted lines are showing the substrate group species. And so we see that as the substrate group species are appearing in the spectra, the water group species are reaching a maxima and then decay. This is much more clear in the 10 monolayer depositions, where as those substrate ions are appearing and peaking, we see that the water group species go through a maxima and then decrease. Next slide. Similarly, for the iron oxide and the pyrite samples, we always are seeing this peak in the water group species appearing, the maxima appearing as those substrate ions are growing in. So next slide. And based on some work that came out of Tom Orlando's group, we were able to determine that this maxima was occurring due to changes in the surface morphology of the water as you sputtered through that thick lice layer and reached the mineral substrates. And so this is just shown sort of pictorially here, where as you sputter away the surface, you end up with little islands of water on the surface, or for the electronic grade silica, there's a very flat surface. You end up with these little islands, whereas for the mineral substrates, which are a bit rougher, you can end up with these little pockets of water.
And that's time.
That's it.
So, Micah, you got to wrap it up.
Yeah, one last slide is my conclusion. Go to the next. Oh, so you skip that. So basically, yeah, we see that we see these secondary ions, and we think that this can be used as a tool to prospect for water on airless bodies containing water.